Picking up where we left off in chapter 2 last time, we looked very briefly at this distillation setup that you might use to distill essential oils. Another way that you can do a separation through a physical change is with filter paper. So in this setup that we've got here, we've got an Erlenmeyer flask down below that's collecting whatever our liquid is. We've got a funnel with a piece of filter paper crammed into it. Probably not how I would have put it in there, but it works. And then whoever's hand this is pouring out some mixture of a solid that's partially suspended in a liquid. And they're pouring that into the filter, and the filter will catch most of the solids up to a certain size, and then the liquid and dissolved solids will work their way through. We'll be doing that in one of our labs, but without filter paper, we'll use glass wool instead. So you've got that to look forward to. A law that I believe we've mentioned before in the class, the conservation of mass. If you remember the guy that was burning stuff in that closed container in that picture, the French guy. That's where we talked about this. That was chapter 0 maybe. So when we do a chemical reaction, matter is neither created nor destroyed. So the matter that we put in equals the matter that we get out when we do a chemical reaction. That's the reactants going to products setup. Since we're doing a chemical reaction, we're going to have some swapping around, some rearrangement of our reactants in our products, some of the elements that are in there. But we should have all of the same atoms that we put in that came out. This would be like if your little brother got creative with your Lego set. They said, hey, that's a really nice set that you've got there, a car, a plane, the Death Star, whatever it is. And they said, let's take that apart and build it into something new. Assuming they didn't eat or lose any of the pieces, you would still have all the parts there. You would just have to pick them apart and put them back together, and boom, you've got your Lego set back. It's potentially a ton of work, more work maybe than you're willing to do, which is also how it works in chemistry. Sometimes you do a reaction, it's really easy to do that reaction, break up some reactants and turn them into a bunch of products, and then if you wanted to take them from the products back to the reactants, it's probably possible, but it might be a lot harder than getting new reactants. So it's often not worth the hassle. Let's say that we burn 32 grams of methane on our gas stove. It will react with 64 grams of oxygen to form 88 grams of carbon dioxide and 36 grams of H2O. We're not doing a problem here, it's just showing you that we've got 32 grams of methane, that's our first reactant, this CH4. It's going to react with 64 grams of oxygen, our O2, and that's mislabeled as 128. Very cool. And it'll form 88 grams of carbon dioxide, and I cut my water in half apparently too. If we double those up, those should now add up, as we see in the example here. So the amount of matter that we had on the left side, 160 grams, is equal to the matter that we had on the right side. They're different chemicals. Methane, you know it being smelly, it actually doesn't have a smell. That's an additive in methane gas. And then O2, that's the oxygen that we breathe, that we need to live, that our fish need to live also. And then CO2, the stuff that we exhale when we're done with our oxygen, and the stuff that plants breathe during the day. And then water, good old H2O. So we've changed the identity, we've changed the properties of the chemicals, but we haven't created or lost any mass. This, of course, assumes that we're capturing and accounting for everything, which in a chemistry problem we can do because it's made up. In real life, that would be harder to do. Let's say that we have potassium hydroxide with the chemical formula KOH, This readily reacts with carbon dioxide, CO2 to produce potassium carbonate and water. So that's a chemical reaction. How many grams of potassium carbonate are produced if those amounts of the reactants react? And 36 grams of water is also produced. So to set up this problem, we need a chemical reaction, because the chemical reaction tells us what things go in and what things go out, and then we can use our knowledge that those masses should be the same to figure out the thing that we're missing. It's kind of like an algebra problem where we've got 4 variables. So we've got some key words in our first sentence. We've got reacts with and to produce. So the reacts with lets us know that things are reacting. They're reactants. So our KOH and our CO2, those are our reactants. We can write the chemical formulas that we were given. We put a plus in between them because we've got both of those things. So those are our reactants. And then we've got this keyword, to produce. So now we're moving on to talking about our products. That means that we can put in a reaction arrow. And our reactants went on to produce products. Our products, K2CO3, and also water. We're not going to worry about how many of each of these molecules we have. We just want kind of like the basic, here's what we've got for reactants and products. And then we can fill in these numbers that we were given. You just match them up with the chemical that it says. So 224.4 grams of KOH. We had 88 grams of CO2. We can put in equals where our arrow is since we're figuring out a mass balance. And the reaction also produces 36 grams of water. So the thing we're missing, the thing we're also asked to find, is how much potassium carbonate, that K2CO3, how much of that do we have? We can make it look really like an algebra problem if we plug in an x there. And then we'll subtract 36 grams from both sides. We need the x by itself. So x is equal to 224.4 grams plus 88.0 grams minus 36.0 grams. And the answer is 276.4 grams. And we can even label it with the chemical, K2CO3. Questions about setting that problem up? Great. You can definitely expect to see one of those on our first exams. And then we're back to the density part, which we talked about previously, so I'm going to skip over it. Calculate the density of a 30.2 milliliter sample of ethyl alcohol. That's the stuff you can drink, the one you'd go out to a bar for, with a mass of that many grams. So we're given milliliters, we're given grams, and we're finding density. Our formula for density, D equals M over V, where M is mass, V is volume. It's as simple as plug it in. So our mass up top, 23.71002 grams. are 30.2 milliliters on the bottom. The number that our calculator gives us, 0.7851. And what are the units?
Grams over milliliters.
Yeah, it's grams over milliliters. They just combine in the way that they're laid out. So the grams over milliliters, can clump those together. And the last thing that we would want to do is check our significant figures. We are doing division. Our top number has 7 significant figures. Our bottom number has 3 significant figures. The one with the fewer number of significant figures is what we take. So we're looking at the 5 is our last significant figure. The 1 tells us we round down. And our final answer, we just drop that 1. All right, there's a little bit about density. Now we'll talk very briefly about energy. We'll come back, I think we'll come back to energy later. We use energy a little bit, but this isn't a physics class, so we don't do a bunch with work, which is also on this slide. So energy is a major component of our universe. We can define it as the capacity to do work. When you have energy, you can do work. When you don't have energy, it's nap time, and then you can do work. Or you power through with coffee or an energy drink or something like that. We also have another term, heat. Heat we'll talk about quite a bit. We have a lab about heat. Heat is a transfer of energy from high temperature to low temperature. Hot things will lose their heat to cold things. So if you open the door during the winter, you're letting the heat out, you're not letting the cold in. And work is defined as force times distance. It might feel like work pushing on a wall. And in the way that we talk about it, if you're just pushing on a wall, the wall doesn't go anywhere, you're still like exerting energy, right? But you're not actually technically doing any work because the wall didn't go anywhere. But it might be a good stretch. Energy is important for us because it helps. It has to do with the way that our matter behaves. And so understanding energy is very helpful for understanding chemistry. Just like that law of conservation of matter that we saw earlier, we have one of those for energy as well. So this is our law of conservation of energy. It's neither created nor destroyed, with some exceptions. So just like matter, the amount of energy that we put into something is the amount of energy that should come out in some form or another. However, we can change our energy from one form to another. There's several forms of energy. We can also transfer our energy from one object to another. And atoms and molecules are doing that constantly. They're constantly bumping around into each other and transferring their energy. And so occasionally you get like a random set of a couple of atoms or molecules that all hit like the same one kind of at the same time. And then suddenly you've got this like really high energy atom or molecule, and then maybe it like gets ejected from whatever thing it's in, or it just bumps into something else, and then it's a whole thing. Yeah, question?
Is this transfer to kinetic energy as well?
Kinetic energy will show up, I think, on the next slide. Yeah, that's related. So kinetic energy is our energy that's associated with motion. I usually wheel across the class for this one. It used to be a lot more fun to wheel across the class because we didn't have carpet in here. But they knew that I was too powerful, and so they put in carpet to stop me. Realistically, though, they put in the carpet because the chairs were incredibly loud without carpet. Just the scraping of the chairs, really, really awful, horrendous sound. So kinetic energy is the energy associated with motion, movement. Potential energy is energy that's associated with position. We usually think of height or composition, like rubber bands. So if I lift something up, I've imparted some potential energy. If I released it, if I let go of it, that potential energy turns into kinetic energy. It falls and it loses that energy. It puts it into whatever it hits. Electrical energy is energy associated with electrical charge, which is confusing to me, just because there's like videos of like, is it really what you think it is? And I don't know. It's beyond me. But electricity, the stuff we're using to power the projector in our phones and the lights and stuff like that. There's also thermal energy, which is a type of kinetic energy. It's the movements of atoms and particles, I'll say. And like air molecules have different amounts of energy based on how hot they are. And then another type of chemical potential energy, or another type of potential energy is chemical energy. TNT notoriously has a lot of chemical potential energy. It's sort of like the chemical equivalent of pulling a rubber band until it's about to snap. And then when you like light it on fire, TNT, not the rubber band, that's like pulling it just a little bit farther and then it explodes to release that kinetic energy, or that potential energy as kinetic or thermal energy. So a bunch of types of energy. And the total energy of a sample is our kinetic or movement energy plus the potential energy. And you can convert these forms of energy, and this dam, the Hoover Dam, is an example, all dams basically are, an example of using kinetic energy and potential energy to our advantage. So a dam holds up some water. Let's see if I don't. It, giant wall of concrete holding back a lot of water. The water starts to pile up in the reservoir. As it piles up, it's building up potential energy. It wants to run downhill. It wants to run through this little canyon, and the dam is holding it back. We're storing up that potential energy, and then you can feed the water through fancy pipes and turbines and stuff. Spin turbines. The turbines that spin have magnets on them, and those induce electrical current in coils or something like that. I'm not an engineer. But that's kind of the basic idea. We take advantage of holding that potential energy, basically like a giant battery, and then whenever they want to or need to, they can let it run through that turbine to produce electrical energy. Now on to stuff that's more relevant for the class, our units of energy. The joule is the SI or metric unit of energy. The font that I used here cuts off the little leg of the J. So the joule, that's our most common unit of energy. We also have the calorie, CAL. This is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. We also have the calorie, CAL, which is equivalent to 1,000 calories. It's also called 1 kcal. Not confusing at all, right? So cal, just to be very clear, is not the same as cal. The lowercase c is smaller. The capital C is the one that you see on the nutrition facts. And then another unit of energy that we have is kilowatt hours. And that's typically the one that you'll see on your power bill. So one of the big takeaways from this slide, there's two types of calories, the little calorie, the big calorie. If you get them mixed up and you calculate for little calories instead of big calories, it's the wrong answer. If you calculate for big calories instead of little calories, it's also the wrong answer. So it's important that we pay attention to our capital letters. It's the little details usually that get people in chemistry. All right, let's convert some energy units. A large light blue sports drink contains 190 calories. How many kilojoules is that? And we have some conversion factors. So we are given flavor text, large light blue sports drink. Love light blue sports drink, one of my favorites. We're also given important information, 190 calories. That's our important given information. And we want to know how many kilojoules that is. So set up, capital C cal, going to kilojoule. You can give your J's a hat. You can leave the hat off. Doesn't matter to me. Can we do this in one step? Yes or no? Yeah, we don't know how to do it in one step. If we ask Google, I'm sure that Mr. Google would do it for us, or Mrs. Google. I'm sure that they would do it for us, but we don't know how to do it. We don't have the tools to do it in front of us. So we're going to need to do this in a couple of steps. Fortunately, we've got a couple of conversion factors given to us in the question. We're given a relationship between big cal, which is what we're starting with, and little cal. That might be a good first step. So big cal to little cal. And we've got this other conversion factor that's got little cal and joules. So that would be a great second step. How do we get from joules to kilojoules? Yeah, we use a factor of 1,000. Whether we multiply or divide, we'll find out. So go ahead and try to set up what that calculation looks like. Give you like 2 minutes maybe, and then I'll go through it. All right, to start off, we've got our 190 cal, big C cal on the left side, and we're going to plug in a couple of conversion factors. Our solution map lets us know. We're going to little c cal first. We want to take the little c cal part of this conversion factor and put it in the top. So 1,000 little c cal, 1 big C cal on the bottom. That gets our cals to cancel, the big C cals, that is. And now we're in little c cals. We're going to go to joules next, and so we're going to put joules on the top, 4.184 joules over 1 little c cal. Little c cals cancel. And then we need to figure out whether kilojoules or joules are bigger. What's a bigger unit? Is a joule bigger or a kilojoule? Kilojoule is bigger, and they're off by a factor of 1,000. The K in kilojoule stands for 1,000. So 1 kilojoule equals 1,000 joules, just like there's 1,000 meters in 1 kilojoule. So we'll put our 1 kilojoule on top and our 1,000 joules on the bottom. Our joules cancel, and this will give us a value in kilojoules. Another fun thing that we can do here, we've got in our first conversion factor, 1,000 up top. In our third conversion factor, we've got 1,000 on the bottom. So if you wanted to, you can just cancel those out. So then you do 190 times 4.184. Calculator says this. We're going to round it for 3 significant figures to 795 kilojoules. Because of the period that I put in. The significant figures is not the important part of the problem. Questions about setting up the conversion? All right, physical and chemical changes often go along with an energy change. For example, water evaporating absorbs energy. Natural gas burning emits energy. An example of a release of energy during a chemical reaction is like if you have a campfire that's burning. This campfire, I think, has like some metals in it. That's why it's got some of the cool colors. So that energy that's released, that's from the chemical reaction that's going on in the fire. When you have systems with high potential energy, they tend to try to lower their potential energy. Low energy is stable. So one way that I like to think of, or that I'll often talk about energy, like for this slide, is that high potential energy or high just energy in general is like running around, moving around. You can do that for a while, but the most stable position, the one I return to every night, is laying down and the little honk shoo me, right? Sleeping. That's the lowest potential energy. We're laying down, we're on the ground, we're in our bed. That's kind of a ground state. And that's going to be a lot more stable. I can stay in that position all night, no problems, as long as there's not too much noise or light. And chemical systems work in a similar way. Things that have high potential energy tend to like to release that energy when they can. So TNT molecules are famously unstable. They're actually not the most unstable. There's things that are less stable. It's just that TNT is convenient because it's stable enough you can move it around, but unstable enough that it explodes. When TNT explodes, of course it releases a bunch of energy, but it also becomes more stable. The same thing is true of when you burn gasoline in your car. You're releasing energy from the chemical bonds in the gasoline molecules to produce mostly CO2 and H2O. CO2 is a famously stable molecule. H2O also, thankfully, fairly stable. We can talk about the way that energy flows in a reaction or in a system. It's either released or it's absorbed. When energy is released, we put this exo prefix on the front. Can anyone think of another word that has exo in the front? Exoskeleton. That's exactly right. What is an exoskeleton? Insects have them, right? We don't have them. It's bones, but on the outside. Your skeleton's outside of your body rather than inside of your body. Just trying to create some word association to help you remember exo versus endo. So in an exothermic reaction, energy is released. For example, wood releases energy when it burns. You can also have endothermic reactions. The endo here meaning inside. So an endothermic reaction absorbs energy. And there's little instant ice packs that you might find in like a first aid kit where you break a little thing on the inside. What happens when you break that little pouch on the inside is you're mixing water and I think it's an ammonium salt. But basically you're mixing salt and water, and it takes energy for the salt to get pulled apart by the water, and so the water rapidly loses a lot of energy. And then it's like, we need more energy for the reaction to proceed, and so it's pulling energy in from the outside, and that's why it gets cold. It also makes it really safe because it's just salt and water. So if you accidentally squeeze too hard and blow it up, it's not a big deal. But the long and short of it is that it feels cold. And sometimes when we're talking about exothermic, endothermic, we talk about the system, and the system is just like the chemical reaction. Basically, it's the little thing that we care about, and then everything other than that is the surroundings. So in our exothermic situation, that's the blue one on the right, our system is the chemical reaction. It's releasing heat into its surroundings. And in the endothermic, it's absorbing heat from its surroundings. So they're just opposites. Each of these processes is either endothermic or exothermic. Question?
Is it possible for an endothermic reaction to become exothermic?
If you reversed it, if it's reversible, then it would swap.
My question was like, say absorbs enough energy to where it starts radiating heat.
You would have to, I don't think that is likely to happen. You'd probably have to switch something about the conditions for it to start releasing heat instead of absorbing heat. All right, each of these things is either endothermic, absorbing energy, or exothermic, releasing energy. What do we think boiling water is? Like if you put water on the stove to make pasta, is that endothermic or exothermic? What do you do when you boil water on the stove? You put a fire under it or you turn on your electric burner, right? You have to dump tons of energy into it. So this is endothermic. Water needs to be heated to boil. What about burning gasoline? When you burn gasoline, is heat produced? Is it exothermic, or is heat absorbed? Is it endothermic? It's exothermic. It's combustion. Produces heat. Candles burning, fires burning, anything burning, combustion, that's exothermic. Now the one that will probably get a lot of people, ice forming on a pond. When ice freezes onto a pond, does it gain or release heat? So this one, we're going from liquid water to ice. Which is hotter, liquid water or ice? Liquid water is going to be hotter, so it has to lose energy to become ice. So ice forming on a pond is actually exothermic. Questions? All right, temperature. Temperature is related to thermal energy. It's a measure of thermal energy. So it's one of the ways that we can tell how much thermal energy something has. We made up temperature scales for that. High temperature means lots or more energy. In the atoms and molecules compared to low temperature. So the more energy that you give something, the more movement there is at this atomic level, this tiny microscopic, submicroscopic level. Temperature is different from heat. So heat is the flow of energy. The movement of thermal energy. Or transfer of thermal energy, and that's going to have energy units. Like cal or cal or joules or kilowatt hours, to name 4. One example of this showing up in your life, probably, assuming that you like cold water, when you put a piece of ice into water or soda, the ice is cold, it can absorb energy from the water. It then melts and turns into water, but it cools down the overall temperature of the drink. Temperature is not a flow of thermal energy, it's a measure of thermal energy. It does require a little bit of heat. So you have to transfer some heat to whatever you're using to calculate or measure the temperature, but they're separate but related concepts. And in this class, in the world, we have 3 different temperature scales. So there's the one that we know, Fahrenheit. Fahrenheit has units of degrees Fahrenheit. And in the Fahrenheit scale, room temperature is around 72 Fahrenheit, sometimes 75 Fahrenheit. It depends on the room. And then the Celsius scale, units of degrees Celsius. This is what most of the rest of the world uses. And room temperature is about 22 or 25 degrees Celsius. There's like a little bit of a range for what's considered room temperature. And then we also have the Kelvin scale, which is just kelvins. So we don't have that degree sign for our units of Kelvin. Some important temperatures to know: the freezing point of water and the boiling point of water are both good to know for the Celsius and Fahrenheit scale. There are conversion formulas for moving between Kelvin and Celsius, as well as between Celsius and Fahrenheit. One way that I've heard the Fahrenheit scale described is it's how your body feels, or how we feel as people. So 0 degrees is super, super cold, and 100 degrees is really hot, and then everything in between, kind of a wash or a mix. So Fahrenheit, you could think of how humans feel. Whereas the Celsius scale is how water feels. 0 degrees Celsius, your water is freezing cold. That's the freezing point. At 100 degrees Celsius, the water is like, yikes, it's hot. Time to get boiling. And then Kelvin is the absolute scale. So if you got down to close to 0 Kelvin, then your atoms, your molecules are basically not moving. They're pretty much at a standstill, and things start to behave really weird. There's fun videos about that all over the internet. For converting between our temperature scales, these are 2 forms of the conversion factors. You will be given these at least on the first exam. Kelvin and degrees Celsius are the same size unit. Fahrenheit is a different size unit. It's a smaller unit. So these are set up to convert from degrees Celsius to Kelvin and to convert from degrees Fahrenheit to degrees Celsius. If you want to go the other direction, then you have to rearrange them. I'm hoping that everyone can do the Kelvin Celsius one. The Celsius Fahrenheit one has a couple more steps in it. I think we're going to see it show up coming up here. All right, we want to convert 47.5 Kelvin to Celsius. So we're given Kelvin, we're going to Celsius, we've got a formula for it. The formula, Kelvin equals degrees Celsius plus 273.15. The problem with the way that this is set up is that it's set up with Kelvin by itself. That means we're solving for Kelvin, so we need to flip it. So we're going to move our 273.15, and that'll turn into Kelvin minus 273.15 equals degrees Celsius. So plug in 47.5 and this temperature is the very, very cold 225.65 degrees Celsius. Questions? Cool. Convert 451 Fahrenheit, or Fahrenheit 451, to Celsius. To do this, we'll need our conversion formula. The way that we were given it is degrees Celsius equals degrees Fahrenheit minus 32 over 1.8. Of course, this is set up to solve for Celsius, and we want to solve for Celsius. So it's perfect. We don't need to do anything. We just plug in our numbers. So degrees Celsius is 451 minus 32 all over 1.8. Please put that into your calculator. And then I'll let you know what I got. Or I'll ask around for some answers maybe. Who would like to volunteer an answer? Yes.
I got 232.8.
Okay, 232.8. Did anyone get a different answer? Yeah?
I got 232.7.
Okay. Did anyone get something significantly different from 232.7 repeating? If so, that's awesome. If you did get something else, that's predictable. So the way that you would get something else, when you put this into your calculator, you might put in this. And what you should have put in is maybe this. So if you use parentheses, that will give you the correct answer. If you don't put in parentheses or do it as 2 steps, you get the wrong answer of 433.2 repeating. Because your calculator did 32 divided by 1.8 first, and then subtracted that from 451. All right, now let's put the two movements together. Convert 115 Fahrenheit to kelvins. All right, 2 steps. First step, convert to Celsius. Plug in our 115. Subtract 32. Divide that by 1.8. It's equal to 46.1 repeating, looks like a T, repeating degrees Celsius. Then we use our other equation. Kelvin equals that 46.1 repeating degrees Celsius plus 273.15 for a total of 319.261 repeating Kelvin. And we're not going to worry about significant figures for temperature problems because it's confusing. I would probably report this as 319 or 319.3. questions about temperature stuff? Another thing that I forgot to mention, Kelvin is never negative. You cannot have negative Kelvin. So if you ever get negative Kelvin, that's a sign that you did something wrong and you should check your work. Degrees Celsius, degrees Fahrenheit, of course, can be negative. Another fun fact that probably will never help you ever in your life in any meaningful way, there's a temperature at which degrees Celsius and degrees Fahrenheit are the same. Does anyone know what number that is? Cool. So negative 40 is the same in Fahrenheit as it is for degrees Celsius. That's just a fun fact. It doesn't really help. But I think it's fun, so there you go. Moving on to some stuff with heat. When you heat something up, it gets hotter. That's kind of a no-brainer, right? But the rate at which it heats up can change pretty dramatically. If you put an empty pot on the stove and you start heating it up, it'll pretty quickly get to be unbearably hot. If you put even just a little bit of water in a pot on the stove and turn the heat up, it'll heat up significantly slower than without the water in there, or if it was just a bigger metal pot. The rate that they heat up changes significantly. The rate that they cool down also changes significantly. So let's say that you go out to a fancy restaurant. You're spending, $100 on your meal for the night. It's a big celebration, something like that. You get mashed potatoes and a steak and peas, let's say. I don't know necessarily why you'd get all three of those things together at a fancy restaurant, but the steak and mashed potatoes is believable. These things are all going to come out from the kitchen, hopefully nice and hot. You paid good money to get your food hot. You didn't come here for cold steak and mashed potatoes. There is a best order to finish these in. Food is generally, in my opinion, like this food, would generally be better hot. Those things will not all stay hot the same amount of time. If I had to guess, the steak is what you'd want to start digging into right away, or bury some pieces of steak in your mashed potatoes. Steak loses heat very quickly, especially compared to mashed potatoes. There's a reason that hot potato is a game and hot steak isn't, partly because steaks are, it would be pretty messy to toss around a hot steak. Peas would be the next to cool down if I had to guess. And then mashed potatoes were going to stay hot the longest. But why? Well, the reason why is because of the water content, roughly. So mashed potatoes has a lot more water in it. Water has what we call a high heat capacity. The heat capacity is the amount of heat that it needs to change temperature of a given amount by 1 degree Celsius. So it's a measure of how much heat it takes to change temperature. And heat capacity is cool, but this given amount part makes it not super helpful. So that would be like specifying if we have 35 grams of water, then it takes this amount of heat. That doesn't translate over well to like if you have 24 grams of water. And so instead, for the most part, we're going to use specific heat capacity. And the specific part of heat capacity is we're specifying a specific given amount. So rather than whatever amount you want, we're saying 1 gram. And that 1 gram makes it a lot nicer. So specifically, 1 gram, how much energy, how much heat does it take to heat that up by 1 degree Celsius or cool it down by 1 degree Celsius? And our specific heat capacity has units of joules per gram degree Celsius. It's usually written out, or it's often written out in that straightforward line version. Secretly, the degree Celsius is also on the bottom. So that's why I wrote it out differently below. And you can look up a table of specific heat capacities for lots and lots and lots of different things. Water notoriously has a very high specific heat capacity of a little over 4, which doesn't feel like a big number, but relatively speaking is a very large number. When you're working on homework problems, you might need this table if you're doing some of the Chapter 2 homework problems. Unless you're asked to solve for a specific heat capacity, you will be given specific heat capacities on the exam. So don't worry about memorizing them. You'll either have a table or you'll be able to it'll be in the problem. So water up here, ruling the world, or at least this world, with a specific heat capacity of 4.184. It takes a lot of energy to raise the heat of water, and that's for liquid water. Other things like aluminum has a value of less than 1, gold 0.129, copper is also on here 0.385. Really low specific heat capacities, they transfer heat really well. They heat up really quickly. That's why you'll often have copper used as like a heat sink or a heat transfer in like computers or other things that need to transfer heat. You may know that it gets really hot here in August, and San Francisco comparatively not so much. And the reason for that is related to specific heat capacity. So we talked about the previous slide, water has a really high specific heat capacity. It takes a lot of energy to heat up water. And around here, generally in August, we don't get too much water around us compared to San Francisco, which is a peninsula, water on 3 sides, and it's cold water. So San Francisco is surrounded by lots of cold water. That cold water can absorb a lot of the heat that it would get from the sun. And so that kind of helps maintain the temperature around the temperature of the water, or at least a little bit closer, versus the land around here, where we don't have a ton of water, is going to have a low heat capacity. There's one place, or a couple of different places that you can go if you want to experience cooler temperatures around here without driving over to the coast. One of those places, if you go to a lake or river, when you go to a lake or a river, there's lots of cooler water. That's going to absorb heat from the surrounding area, and so your average temperature is going to be lower. Or a cornfield. If you're ever driving around the countryside with the windows down at night in the summers, and you suddenly feel like, ooh, kind of like dropped a couple degrees there for half a mile, good chance that you drove past some irrigation, like a cornfield. Corn has a lot of water in it. It's pretty dense. That's going to drop the temperature of the surrounding air. All right, we can use this equation to do some heat and temperature change calculations. So Q here is heat. M is mass, C is specific heat capacity, and delta T is change in temperature. So that triangle is delta. And that means change in. Since it's right before T, change in temperature. And that delta T, the change in temperature, is either in Celsius or Kelvin. They're the same size unit, and so it doesn't matter which one it's in. And the change in temperature formula is the final temperature minus the initial temperature. And it's common to use these little subscript F's or I's to indicate final or initial. So TF minus TI is change in temperature. All right, we can use this formula to solve questions like this. The question is, what quantity of heat is transferred when a 150-gram block of iron metal is heated from 25 degrees Celsius to 73.3 degrees Celsius? Follow-up question, what is the direction of heat flow? What are we given? We're given a mass of metal, iron metal. We're also given some temperatures. And what are we being asked to find? Quantity of heat transferred. And we'll also be asking direction of heat flow. We're going to be using our new favorite formula, Q equals mc delta T, where delta T is the final temperature minus the initial temperature. So we're trying to find Q. We've been given a mass, and we've been given two temperatures, which we can use to find delta T. Is there anything we're missing? Yeah, we're missing C. We're a bunch of landlubbers. And so we'll need to go to a table to find our C value. So I'm going to jump back to that slide now. Go. Our metal here was iron. So that's 0.449. And we're jumping back. 0.449 joules per gram degrees Celsius. All right, so we have, in theory, all the numbers we need to solve the problem. All that's left to do is do it. Which temperature is our initial temperature? Is it 25 or 73? 25 is our initial temperature. And 73.3 is our final temperature. So we can calculate our delta T. It's 48.3 degrees Celsius. And then we can plug that into our Q equals MC delta T. So Q equals our mass of 150.0 grams times our C value, joules per gram degrees Celsius, times our 48.3 degrees Celsius. And we need to make sure that our units cancel out. So looking at our grams first, we've got grams in our C, we've got grams on the bottom. Those will cancel out, very nice. And we also have degrees Celsius and degrees Celsius on the bottom. So those will also cancel out. The units that we're getting here are joules. Are joules a good answer or unit for this question? Yes. The answer is yes. It didn't say what unit to give, so joules works. That is a quantity of heat. If we were asked for the heat not in joules but in kilojoules, we would do a conversion, or if we were asked for it in calories or calories, those two, it would also be different units. So it's important that we pay attention, if we need to what the units were asked for. I'm mentioning that specifically because it's often a point of consternation on the exam, first exam, because they're like, oh, I calculated it, I got joules, but the problem asked for it in kilojoules, and so it's the wrong answer. So I'm just letting you know that explicitly right now to keep that in mind. So 3,253.005 joules. We get the joy of rounding this to three significant figures. 3,250 joules, which gets to be written as 3.25 times 10 to the 3 joules. And then the direction of heat flow. Is this endothermic or exothermic with respect to the block of iron? Is heat going into or out of the iron? Into. Heat is going in. There's two ways that we know that it's going in. The first way that we know is the temperature went up. We must have added heat to the temperature up. The other way that we know is that our joules is positive, which is related to the temperature going up. Any last burning questions before we wrap up? Yes? That's a great question. I don't know where the attendance sheet is. Who's got it? It's over here. All right, that'll do it for class.